In this video, we're going to be discussing acid-base titrations, a process used to determine the unknown concentration of an acid or base solution. Let's start with a quick rundown of the learning objectives of this video. We'll start with a definition of what a titration really is. We'll then talk about the setup. A titration is an experimental process used to collect specific data. We'll talk about how that's set up, and we'll talk about the equipment and chemicals used in the process. We'll then dive into the actual procedure that goes along with this, and finally we'll wrap up dealing with the calculations that go along with it. The data has to be processed in order to eventually come up with the solution we're looking for. To begin with, a titration is an analytical process used to measure the concentration of an unknown sample. Now, out in the chemistry world, there's actually lots of different types of titrations. We will primarily be interested in this type right here, which is an acid-base titration used to determine the unknown concentration of an acid or base. But you can also do other titrations. Gravimetric titrations create precipitates, like we talked about earlier in this chapter. And then recording the mass of that precipitate allows us to determine concentrations. And then you can get into the more exotic stuff like things called complexometric titrations, which are very specific types of chemical reactions that aren't neutralization, but still have the same process of determining the unknown concentration of a solution. And the list goes on and on and on. As I said, we're primarily interested in acid-base titrations, but I think it's nice to know that there are other methodologies out there. All these methods use the data collected as a tool for calculating the concentration of an unknown solution, and ultimately that calculation is going to come into something we're very familiar with, known as solution stoichiometry. So the great news is we're not really going to be introducing any new mathematics in this particular topic. Let's talk a little bit more about the actual process of a titration. We're going to take a known base where we know its concentration, and we're going to mix it with an unknown acid in order to determine the concentration of the acid itself. Now the neat thing about this is this is going to react in the form of a neutralization reaction where the acid, HA, so this is our acid, is going to react with our base, BOH, to form a salt and, as always, H2O. This relationship between the acid and the base is very, very predictable because it's happening in the context of a balanced chemical reaction. And because of that predictable relationship between the amount of base used and the amount of acid that must be present, this should sound familiar because this is basically the basis for how stoichiometry works. We can mathematically relate the amount of acid to the amount of base with stoichiometry. So then the process as a whole then is all about collecting the right amount of data so that we can then use that stoichiometry to create this relationship. And again, that math is going to come in the form of something we know as solution stoichiometry. We're going to use the concentration of a solution to convert between the volume of that solution and the number of moles. If you remember this diagram from earlier in the year when we did stoichiometry and mole conversions for the first time, we're going to be focusing on this conversion. And again, the link between the two of these things is going to be that concept of molarity. If you need a quick review of how these conversions work, please go back to the beginning of this unit and watch the first video on solution stoichiometry. In our solutions, the acids and bases will be acting together in the neutralization, and knowing one of those concentrations will allow us to calculate the other via stoichiometry. So as a quick preview of what this mathematics is going to look like, I can show you what an example kind of problem is going to be. We're going to be asked to determine the concentration of 20 milliliters of an unknown solution of hydrochloric acid after it was titrated with 27.31 milliliters of a 0.124 molar solution of potassium hydroxide. I do not expect at this particular point in time that you can do a calculation like this, but I should be able to show you the mathematics associated with this calculation, and what I'm hoping is that it looks familiar. So we can take, first of all, the balanced chemical reaction, and we're seeing all one-to-one ratios. And then from that balanced chemical reaction, we can then start putting together the actual stoichiometry itself. If you notice, we begin with the volume of the base, and we'll denote that as V sub B. That was told to us right up here in the problem. We convert that into liters using this step here, and then here's that solution stoichiometry step. We're converting the volume of base used into the number of moles of base present using the molarity that was told us. So this would be the molarity of the base. Then we use our mole-to-mole ratio from the Bounds chemical reaction. 1 mole of HCl reacts completely with 1 mole of sodium hydroxide, and this tells us that there are 0.00339 moles of hydrochloric acid that would react with our 27.31 milliliters of base. Now that's the number of moles of acid. The question, however, asked for concentration. Connect this to something more recent in our unit, and we can think of molarity then, our measure of concentration, as moles of solute per liters of solution. Well, we have our moles of solute data right here, which we can plug into the top half of this equation. And up here in the problem, we were told that the volume of our acid solution was 20 milliliters. And we can plug that into the bottom of our equation to get something that looks a little like this, and ultimately end up with the concentration of the actual acid in the solution itself. So what we can see here, even if that was hard to follow along with, is through mathematics we've already done in this chapter, solution stoichiometry first and a molarity calculation second, we're able to do the titration calculations to determine the concentration of an unknown acid solution based on the data provided in this problem. By the time we get to the end of this section, you'll be able to do these calculations on your own, but again, what I wanted you to see here was the relationship between what information comes from a titration and how the math we're already familiar with in this chapter allowed us to turn that information into an answer, into a concentration of the acid. Now let's turn our attention a little more to the actual data and the setup that we're going to be dealing with here. As a kind of a cartoon picture over here on the left, we can see what a titration looks like. We're going to be using a special piece of glassware known as a burette. It is a long, thin piece of glassware that has a valve on the bottom known as a stopcock. This allows us to open and close the valve and let the solution inside the burette slowly into the container below. Inside the burette, we're going to place a base with a known concentration. This is going to be our BOH substance from the reaction we've written before. In the Erlenmeyer flask at the bottom, we have an acid with an unknown concentration. This is our HA from the reaction before. And our job then is going to be to collect the following data. First of all, we're going to need to know the molarity of the base, and this is usually either given to us or something that we figure out in the course of the experiment. So we'll say that this data is going to be given. The volume of the base is the job of the burette. As we dispense the liquid from the burette and it drips into the reaction down below, there are measuring markers here that we can use to measure this. So this is going to come from our burette. And finally, the volume of the unknown acid is whatever we place down in here, and this is usually going to be measured using something known as a pipette. That will allow us to measure a very specific volume of the acid and place it in there. Having all that information known, that'll eventually allow us to calculate the concentration of the acid, or as we'll refer to it later, M sub A, for the molarity of the acid. Now the next step in the process then is, how do you know how much of that base to actually add? Well, what we're shooting for when we add the base is something known as the equivalence point. This is the ideal outcome of our titration. This is the point at which we added the exact amount of volume of base needed to completely neutralize the unknown amount of acids. We can think of this as stoichiometric relations between the two of those, and this is exactly the data we need to do the related stoichiometry we also talked about. Unfortunately, this is difficult to observe directly. There are tools that we can use. A pH meter, for example, would allow us to get this job done, but if you're just trying to visually see this, we can't see an equivalence point happen. As a result, there's another place we can shoot for. The other option in doing a titration is something known as the end point of the titration, and this is what we're actually going to be measuring in this experiment. This is the point in the titration when you're told by a chemical indicator, and we'll talk about what that is in a second, to stop adding base. And what happens with the end point is you'll get a visual change in color, and that change in color says you've gotten to the end of the titration, and as a result, you should stop adding the base in. The beauty of, or the downside, I guess, of an endpoint is that it's an approximation. It's not exactly what we're looking for. Remember, what we're ideally looking for is this guy right here, the equivalence point. But this approximation is something that we can very easily observe because it's going to come in the form of a very bright color change. And because it's easy to observe, it's still going to get us some very good and very reliable data. Now let's talk a little more about this concept of a chemical indicator, because if you recall, that was the substance that we used prior to identify when our end point of our titration was. A chemical indicator basically is any chemical that changes color at a specific pH value. And depending on which pH value you want to find, there are different chemical indicators out there that change pH at different times. This chart you see on the left side of the screen is basically an arrangement of a bunch of different types of indicators. And over here on the y-axis, we can see what pH they change color. For example, if you wanted to figure out when your reaction changed color right around pH of 4, an indicator like methyl yellow is a good choice because it changes color right at 4. It goes from this bright red to a yellow color here. The indicator we're going to be using primarily in our experiments is this guy right here, phenolphthalein, one of the most commonly used indicators when you're working with strong acids and strong bases. It changes color right around pH 8, which is a little bit higher than what we normally want, but it has a very bright and vivid color change, which makes it very, very easy to spot. When you're going to do your actual titration then, the big goal is to choose an indicator that matches your equivalent point as close as possible. If at your equivalent point, your pH of your solution is right about 8, you want to choose the indicator that changes color right about 8. This gets your endpoint, which is shown by the indicator, and your equivalent point, which is determined by the chemistry, to be as similar to one another as possible. And as a result, what this ultimately does is it's going to reduce error in your experiments. The closer your endpoint and your equivalence point are, the more your experiment will accurately reflect what's actually happening in the flask. If you're interested in a copy of a chart that looks like this, they're very easily available online. If you search the terms chemical indicator chart, you'll find a lot of documents that look just like this, some that look different, all with very similar information. So the next question is what does this look like when we actually do it in the lab? Well, here's what your glassware setup is going to look like, at least a close-up of it. Right here we have the burette, which is used to dispense the base into the solution. Right now, this solution is primarily an acid, and we know that because the color is clear and phenolphthalein is clear in the presence of acids. As you add more and more of base, eventually the acid will be consumed, the pH will suddenly jump up to a much higher number, and you'll now have a solution that is filled with base, and we can see that because of the color change. Our job is to get to the point where we just start to see this happen, and what you're going to be looking for is this very light pink color, and this is going to be our endpoint. Just as the solution starts turning from acid into base, we get this faint pink color, and this is the place you're looking for. And if your reaction's set up very carefully, your endpoint will also be very similar to your equivalence point, and it will provide you with the necessary data needed to do the stoichiometry calculations in order to determine the concentration of your unknown acid. So we'll wrap up then with a quick discussion of what these calculations are going to look like. I showed you in the beginning of the video how those calculations work using the full-blown solution stoichiometry. But the good news, and here's where I think things are going to start to become a little more positive here. The good news is that the stoichiometry always has the same exact data in it. And as a result, it's always going to be the same exact setup. If the setup is exactly the same every single time, why go through the trouble of setting up a stoichiometry calculation when we can instead simplify the entire process into an equation? And that's exactly what we can do here. Capital M sub A is going to be the molarity. Capital V is going to be the volume. And this volume has to be in liters. And N is going to be the coefficient of the balanced chemical reaction. The A's and B's then stand for acid, and B stands for base. So half of this equation is about the information associated with the acid, the other half is the information associated with the base. And when you're dealing with N's, this is the coefficient in front of the acid in the balanced reaction, and this is the coefficient in front of the base in the balanced reaction. Now let's take a moment and see if we can't prove that this equation is indeed a representation of all the stoichiometry that we did earlier in this video. And what I have up on top of the screen here is that same exact stoichiometry again. Again, here is our stoichiometry calculation that determined for us the number of moles of HCl, and then that data was plugged into the molarity equation divided by the volume to ultimately calculate our final answer, which is our molarity of acids. Well, if we start labeling what some of these data values actually are, we can see how this thing starts piecing together. For example, this was the volume of the base of the solution, and this guy was the molarity of the base. These two guys here are the mole-to-mole ratio, which is really a representation of coefficients. This would be N sub A on the top. This would be N sub B on the bottom. And then last but not least, all of that's going to be divided over here by the volume of the acid that was used. If we take all that information, take out the numbers, and replace it with the actual variables, we're going to get a setup that looks like this. The volume of the base times the molarity of the base times the mole-to-mole ratio. That told us how many moles of product there were. The moles of product divided by the volume of the product eventually calculated the molarity of the product. We can use our algebra to clean this up a little bit to get an equation that looks like this. And then we can use algebra again to move some variables around. For example, we can move the volume of the acid over here. We can take the moles of acid and divide that by both sides. And ultimately, we end back up at the equation that we talked about before. I just wanted to make sure that we see that there's a clear link between the math that's going on here in forms of stoichiometry and the simplified equation that we can now use. So I might ask you at times to do these calculations using the solution stoichiometry, but generally speaking, this is a much simpler way of getting at exactly the same answer. To wrap things up, we have a second example calculation problem. Unlike the first one, I think it may make a lot of sense to use the equation in this particular scenario. You are going to need a balanced chemical reaction for this, and we have it shown there below, but this is definitely something I do expect that you guys should be able to figure out on your own. With the balanced chemical reaction, it's probably not a bad idea to pause the video, give this particular problem a try using the equation. When you unpause, I'll have the work done for you as well as the answer that goes along with it. So here's our equation, m sub a v sub a over n sub a equals m sub b v sub b over n sub b with the appropriate numbers plugged in. I've got the volume of the acid, which was told to us as 25 milliliters plugged in here. I've got the volume of the base, which was told us as 37.85 milliliters plugged in here. We're told the concentration of the base, which gets plugged in here. Molarity of the acid is what we're solving for. And then last but not least, these coefficients here, the 1 and the 2, end up being the subscript values for n. That got a little messy, but all we're doing is plugging the appropriate numbers in the appropriate place. Algebraically, you could then solve for m sub a, and you find that m sub a is 0.5678 molar solution of sulfuric acid. So again, from data collected via stoichiometry, this is what this is here, from titrations, we can plug that data into the formula down below and then ultimately determine the concentration of an unknown acid solution, which, if you recall, is exactly the purpose of a titration. That wraps things up for today. At this point in the game, you should be able to do a couple different things. First of all, you should be able to tell me what the purpose of a titration is as a measuring tool. What is its job? You should be able to briefly explain the setup and the equipment of a titration. I think that's something a lot of us will be a lot better with during this week as we work on titrations in class. You should definitely know the difference between an equivalence point and an end point. There's a subtle difference there, but you should be able to talk about it. And lastly, but not least, you should be able to calculate the concentration of an unknown acid or base solution using titration data. And I do expect that we can do those calculations using solution stoichiometry and the titration equation itself. I don't necessarily feel at this stage in the game you guys might be 100% on this last bullet, but we are going to spend time in class doing problems together. We're going to spend time in class doing a simulated titration, allow you to collect the data and practice with that, and then we're actually going to do a real titration hopefully by the end of the upcoming week.